let's talk about how to use conditional probability within the context of discrete random variables. So recall that for a general probability space, where we have some kind of sample space, event space, and probability measure, in that context, we've defined and played around with this idea of conditional probability. Okay? So the idea of conditional probability is you have an event A, and you're trying to determine its probability given that another event B occurs. And we define that to be the probability of A given B, which is the probability of A intersect B divided by the probability of B, assuming the probability of B is positive so that we're not dividing by 0. And we also define the PMF for discrete random variable x. So that was just, the PMF is the probability of seeing an outcome that maps to a particular value little x in the context of the random variable. Okay, so those are two of the things that we've already defined. And how can we think about conditional probability within the context of a PMF? Well, the most useful thing we can define is a conditional PMF, P of x given B of little x. So this is the conditional PMF of x given the event that x falls into the set B. Okay, and this is defined as follows. It's just the conditional probability of seeing an outcome that maps to little x given that we know x falls into B. Okay, so this is kind of an abstract definition. We'll usually just set it aside and go with one of the following simpler formulas. Okay, so here we go. So basically, if x is an element of B, then we write this as the probability of x divided by the probability of x falling into B. And if x is not an element of B, then it's just 0. Okay, a different way of writing the same thing is just to write the PMF divided by the sum of the PMF over B, if x is in B, and 0 otherwise. Okay, and all of this is assuming that the probability of x falling into B is in fact positive, right? So we're not dividing by 0. So the idea here is that it's basically the same as the PMF, except now that we know x falls in B, those are the only values of the PMF that are allowed to have positive probability, because we already know it has to go into B. And the reason we divide by the sum of the probabilities over B is to renormalize the total probability of 1. Okay? Very simple. Let's kind of go into a little more detail to see why this is true. So let's write out the definition of the conditional PMF in the abstract form. And let's call this first thing event A, and let's call this second thing event C, since we're already using B. So then this is just the probability of A given C. By the definition of conditional probability, that's probability of A intersect C divided by probability of C. And now we're going to plug back in the events A and C. Okay, so we plug back in A, here it is, we plug in C, and then we divide by probability of C. Okay, so we've used the definition of conditional probability, and now we see that this first term simplifies quite a bit. So the numerator simplifies in the following way. We're left with just the probability of an outcome mapping to a value little x whenever x is in B. Okay, so the intersection is what ensures that x actually falls into B. Okay, so only outcomes in B actually occur. And so if you're not in B, then you have probability 0. Okay, and how does this simplify further? Well, this thing on the top we should just recognize as the definition of the PMF, right? So when we defined the PMF a while ago, that's how we defined it. So really it's just the PMF divided by the probability of B, and by additivity, the probability of x falling into B is just the sum of the PMF over B. Okay, so that's it. That's how we got those two formulas. Those are the ones we're really going to be using, and this abstract definition at the top here, we're going to kind of sweep under the rug most of the time. Okay, I've hinted at this, but let's say it formally. So the conditional PMF has all the properties of a normal PMF, so it has non-negativity, right? So you can't have negative values. If you sum it up over B, or even over the whole sample space, you get 1, so it has normalization. And for any event C, the conditional probability that your random variable falls into C, given that you know it falls into B, can be calculated as follows. So the probability of x falling into C, given that it falls into B, is just the sum over C of the conditional PMF given B. That's additivity. And we could go further. We could develop versions of the multiplication rule, the law of total probability, and Bayes' rule, right? So we could do all of those things, but we're just going to leave that to the lecture notes, and you can go and look that up. Okay, so we're not going to spend time on that here. So what we want to understand is, given that the event B occurs, meaning that X falls into B, what is its average value? So how has the average changed once we learn this information? So we need to generalize our idea of expectation to handle conditioning. That's it. So we're going to do that. Okay, the conditional expected value, E of X given B, so if this is the conditional expected value of X given event B, is just the sum over B, X times the conditional PMF. So the way it's modified from the usual expectation is now I'm only summing over B, and I'm using the conditional PMF given B, not the original PMF. We could also define the conditional expected value of a function, g of x, right, given B. And in the same way we were dealing with functions before, all I'm going to do is just plug in the function times the conditional PMF and sum over B. And we have linearity of expectation, so that's always going to apply here. So we have E of AX plus B given big B, and we can pull out the little a in the B. And finally, the conditional variance of X given B is defined as follows. Okay, so I'm going to write this out and then we'll talk about it a little bit. Okay, so here it is. And so notice that what I've done here is taken X and subtracted its conditional expected value, squared it, and then taken the conditional expectation. Okay, so every place where I had an expectation, there were two, I replaced it with a conditional expectation. I could also develop the alternate variance formula, so I could have E of X squared given B minus E of X given B squared. The key thing to remember with conditional variance, which is a little tricky to keep in mind, is that you're always conditioning on B every time the expectation occurs. Let's do an example. Okay. So in this example, I'm just going to draw my plot for the PMF, and we're going to have positive and negative values, right? So here I'm just drawing my x-axis, and we're going to have values that range that are basically going to be a sixth and a third. And here's my original PMF, okay? So it's going to have a value at 1/6, then 1/3 at -1, then 0, then a sixth, and then again a third. So that sums up to 1, which is good. Okay, so I can just write this out case by case if I'd like. So we can see both versions, the plot and the case by case. So I have a third when x is -1 or +2, a sixth when it's -2 or +1, and 0 otherwise. So for any other values, it's 0. Okay, now let's condition on the event that the absolute value of x is strictly greater than 1, okay? So this is a perfectly fine thing to condition on. The main thing that we need to do is translate this into membership in a set. In this case, let's call the set B, which we're going to draw in red. And we'll notice that, so we need to think what elements of the range of x satisfy this condition that its absolute value is strictly greater than 1. And looking at the plot, I can see that the elements are going to be -2 and +2. So it's equivalent to write the condition that the absolute value is strictly greater than 1 as x belongs to this set B. And no matter what kind of interesting conditions we come up with for random variables, remember that we can always translate those into memberships in some particular set. And that's always going to be helpful for us when we're doing calculations. So it's convenient for setting up problems and evaluating applications to have kind of generic conditions. But when we're doing the actual calculations, we want to translate them into membership in a set. Okay, we have B, so let's just draw which elements are in B on the plot. So these are the elements of B. And now what I need to do is calculate the conditional PMF. Okay, so I want to understand what is the conditional PMF now that I know that x is an element of B. Okay, well, let's write down the definition. Conditional PMF of x given B is defined to be the PMF of x divided by the probability that x falls into B. And that's going to hold whenever little x is an element of B, right? And the rest of the time it's just 0 because we know x has to be an element of B. Okay, so what is the probability of x falling into B? Well, by additivity, I can just sum up the values of B and I just sum up the PMF. Okay, I sum over the values of B for the PMF and I just have the probability of x being -2 plus the probability of x being +2. So that's going to be a sixth plus a third, and that's a half. Okay, So now I can divide through by this value, and what it effectively does is rescale the PMF on the positions of B by 1/2, which is 2. So it's like I'm multiplying a sixth by 2 to get a third, and then a third by 2 to get 2/3, okay? And the other values at -1 and 1, those have probability 0 now because they're not in B, okay? So I keep the shape of the PMF the same on B, but I renormalize. Okay, so I can just write this out. So the conditional PMF of x given B is just going to be 2/3 when x is equal to +2, and it's going to be a third when x is equal to -2, and 0 otherwise. Okay, and I can see now that, so x really does belong to B in this case. So as I just said, the shape of the PMF is always the same as it was originally on the points that fall for which x falls into B, and otherwise it's 0. And the only change is that on those points, I'm just renormalizing the values so they sum up to 1. So it's a valid PMF, in this case, a conditional PMF. Okay. All right, let's calculate the mean and the conditional mean for this same example. Okay, so the mean, we're going to write out the formula. So we just sum up over the range of x times its PMF. So we weight the values of x times the PMF values. So in this case, just looking at the plot, I'm going to get -2 times 1/6 plus -1 times 1/3 plus +1 times 1/6 plus 2 times 1/3, and that's a sixth. Okay, for the conditional expectation of x given B, I'm going to sum up over the values in B only, x times the conditional PMF of x given B. That's the definition of the conditional expected value. So I get -2 times a third plus +2 times 2/3. Okay, and that's 2/3. Basically, this makes sense because I see that there's a little bit more weight to the right, so I expect the center of mass to have drifted a little bit to the right. Okay, let's do an example that also uses families of discrete random variables. Okay, so what we're doing is we're just waiting around. So I'm at my factory. I'm waiting for the delivery of a missing part that I need to complete my system. Okay, and I don't really have a great idea of when it's going to arrive. I just know it's guaranteed to arrive within 20 days, but I don't have any more information. So let's just say it's uniformly distributed over 1, 2, up to 20. Okay. Let's say that I've been waiting for quite a while now. So I've been waiting and it still has not arrived, and it's been 6 days or 6 time slots. I still don't have it. So what I want to do is I want to recalculate now what is the conditional PMF with this new information, and what is the conditional expected value and the conditional variance. Okay, so all of those are conditional. I just didn't write conditional in front of each one since I didn't have space. So B in this case, what is B? Basically, it's that I've waited more than 6 slots. So based on the range, it's going to be 7, 8, up to 20. So those are the values that are larger than 6. So then if I sum up the PMF over B, I'm summing up from 7 to 20 and plugging in the PMF value. And since it's uniformly distributed, the PMF value is just 1/20 since there are 20 values. And so I get 14/20. Okay, so now let's go ahead and calculate the conditional PMF. So the conditional PMF, as we've seen before, I can just use this formula, which is the PMF value divided by the sum over B of the PMF. So I'm renormalizing by the probability of x falling into B when x is in B and it's 0 otherwise. So in this case, it's going to be 1/20 for the PMF divided by 14/20 for the conditional PMF. That's 1/14. That happens when x is 7, 8, up to 20, so it falls into B, and otherwise it's 0. For the conditional expected value, I again just use the formula, which is going to be summing over B, x times the conditional PMF. Okay, and so summing over B is 7 to 20, x times 1/14, and so that's 7 plus 20 over 2, and that's going to work out to be 27/2. All right, and finally, I can kind of notice here that this conditional PMF actually is itself from a family of discrete random variables that we've studied, it turns out to be a discrete uniform random variable that ranges between 7 and 20. Okay, so this conditioning on B has just modified the effective range of my random variable, but I'm still free to use the formulas that I developed for discrete uniform random variables. In this case, it's going to be convenient because if I want to get the conditional variance given B, I can just use this formula, which is B minus A plus 2 times B minus A divided by 12, right? So that's something that we developed. You can go back and look it up. I just plugged in those values. I get 15 times 13 over 12, which is 65 over 4. So why was this nice? It basically saved me from having to calculate 14 different terms in a summation, which would have had x minus 27 over 2 squared times 1 over 14. So I would have had to go and do all of that calculation. And this lookup in the, of the variance for discrete uniform random variable helped me save that. Okay, finally, let's do an example that uses a binomial family of random variables. So x is going to be binomial with n equals 5 and p equals 1/3. And let's just say that the set B is 0, 1, 2. Okay, so our goal is just going to be to compute the conditional PMF of x given that B occurs. So given that x falls into B, to be more precise, and the conditional expected value as well. But first, the PMF. So the PMF of x is just 5 choose x times 1/3 to the x times 2/3 to the 5 minus x for x going 0 up to 5. And it's 0 otherwise. Why is that? Well, remember that the PMF for the PMF for a binomial random variable, if you go back and look it up in the previous video, it was n choose x, and here n is 5. And it was p to the x, here p is 1/3, and 1 minus p, 2/3, to the n minus x, which is 5 minus x. Okay, so that's how we got this. And to get the probability that x falls into B, we're just going to sum up over B. So we're summing up the PMF at 0 and at 1 and at 2, right? And so that's going to be plugging in 5 choose 0 times 1/3 to the 0 times 2/3 to the 5 plus 5 choose 1 times 1/3 to the 1 times 2/3 to the 4 plus 5 choose 2 times 1/3 to the 2 times 2/3 to the 3. Okay, and I could add an extra step where we kind of work all of these fractions out carefully, but instead I'm just going to jump to the answers. It's going to be 32 over 243 plus 80 over 243 plus 80 over 243. You can check for yourselves. That's 192 over 243. And remember that these are the values of the PMF at 0, 1, and 2. And the reason I'm pointing that out again, just so we can reuse these computations in a minute. Okay, so the conditional PMF is going to be the PMF values, right? So P of x divided by the probability of x falling into B, which we've just worked out. And that's going to happen when x is in B, and otherwise it's going to be 0. So when x is equal to 0, our PMF value is 32 over 243 divided by the probability of x falling into B, which is 192 over 243. Otherwise, it's 80 over 243 divided by the probability of x falling into B when x is 1 or 2, and 0 otherwise. Okay, so we can simplify these. So the first one just simplifies quite a bit. It's turning out to be a 1/6 when x is equal to 0, and the other two are 5/12 for x equals 1 and 2. So this is a nice, simple conditional PMF that we worked out. And in fact, if you went and worked out the original PMF values, plugging in each value of x, you'd also get some pretty simple fractions. But we didn't do that explicitly for every value because we actually didn't need the values at 3, 4, 5, so that would have just been a waste of computation. Finally, let's get the conditional expectation. So I'm adding this to my problem statement up here. And so I'm just going to use the formula. So I'm going to say that the conditional expectation of x given B, I need to sum up over B, x times the conditional PMF given B. So that's going to be 0 times a 1/6. We just worked that out, plus 1 times 5/12 plus 2 times 5/12, and that's going to be 15/12. And that's going to simplify to be 5/4. Okay, and that's it for this example, and that is it for conditional PMFs and conditional expected values.